Okay, good morning. Today, I believe I can fix our final schedule for all the remaining of the classes. I just give you a little announcement, okay? The first thing is we currently, this lecture, we're going to finish the mining data streams, but we get into mining spatial, temporal, and the social media, okay? And in the meantime, I first should say the review due is this Sunday, okay? After that, the our TAs are going to evaluate your review, give you the score, but in the meantime, we'll select a few really good ones. We allocate the 1 whole week time. That means we have 2 lectures, likely select 8 to 10, depends on how good and how the TA evaluate your survey report. We'll have 2 lectures to allocate to your presentation on the survey report. Okay, that's also we need your slides as well. We can evaluate not only on the report itself, but also on the set of slides. Okay, and if you look at this, we actually moved down a little on the contents. We finished the stream data mining, but we will allocate some time on advanced classification, okay, essentially pattern-based classification. We introduce this. Then we finish all the lectures, okay. Then the assignment due is on Tuesday, April 26th. Then the midterm exam is on the 28th, which is Thursday, okay. After this, in principle, next Tuesday, the Tuesday, May 3rd, will be another class, but we are not going to have it. We are going to move this class to the final presentation time because it will give you a little more time for your preparation. But then for the final course project presentation, we have essentially it's May 5th, which is a reading day. In the afternoon, we will have 2 sessions. Then on the Monday, May 9th, the whole day will be our presentation time, okay, for all the course projects. I actually printed out a sign-up sheet because I do not know how many groups we will have, because some are individually as a group, some 2 people as a group, some 3 people as a group. I want to know how many final projects will be presented, so we will be able to allocate the time. Okay, so the presentation time you can see is May 5th, Thursday. We will have 2 sessions. 2 sessions essentially will have 10 project presentation, and 9th, we plan to have 4 sessions. That means we will have 20 project presentations or a little more. Okay, so our distribute this. Every group, no matter how many people you have, will only have 1 slot. If you are the group lead or you sign it, the other people will not sign it. I will distribute this. You don't need to write your project presentation title and abstract. Later, I will ask you to load it by yourself to the website. But I will need your group, all the members of your group. That means if you are the lead or you're the first one, sign it. You sign all the names and net IDs of this project. So we'll know how many people sign up, how many people probably missed a class, did not sign up. Okay. So that's the one we are going to do it in this class. You just pick up a slot representing your group, okay, and write down all the names. So we are going to see whether we have enough slot or we need more time, more slot to open up for presentation. Okay. The presentation is 12 minutes per group. Okay. So we actually will allocate 15 minutes, including question answering, including shuffling. So essentially, it's 12 minutes as your presentation time. Okay. So we will send this to everyone. So you are going to sign up for your group. Okay. There are lots of slots. There are about more than 30 slots. You try to find the right one. Put it in. Okay. So that's about our final project. The final project due time, we plan to have the due time is on Tuesday, end of Tuesday, May 10th. Okay, we will see, whether this is a good time, but we have limited time to grade, and I also know the grading will be done by the whole group. Some students may have to leave, right after the exam week, so we cannot postpone it. I think the deadline will be May 10th, 11:59 p.m. Okay. Of course, you are welcome to submit earlier. Okay. Any questions regarding all the final things we need to do? Okay. We have lots of things. Survey report this weekend. Then we get assignment 2, midterm 2, and the final projects. Okay. So there are lots of things. A lot of grades. Actually, the result will come out within these several weeks. So you really have to work hard in these several weeks. Okay. Any questions regarding this? Yes? Yeah, the first thing is all the group members need to be in your presentation for sure, but you don't have to come up. We welcome all the people show up, okay? But if you say, one person show up representing the whole group, that's also fine, okay? And for attendance, because you are going to grade, we plan to require everyone to attend half of all the presentations. That means you are going to grade half of the ones. Including yourself, you must be there, but you are not going to grade your project. Okay, then you need, I think total we have 6 sessions, A, B, C, D, E, F. Later, we still distribute the same sign-up sheet for every session, but you need to attend half of the session. Of course, you are welcome to attend more. Okay, that means you attend those sessions, you will be responsible to grade them. Okay. Any questions? Okay. Remember, the grading will be done by half of the scores will be graded by the peers. Half of the score will be graded by me and TAs. Okay, we try to be fair. Okay. And based on the past experience, it is very fair. Overall, the group consensus is very consistent with TA and my consensus. Okay, so that simply says if you did well, everybody will say you did well. Okay, of course we remove the top or bottom outliers. Okay. Hopefully you enjoy the class and also enjoy your project. If you have any other questions regarding your project, for example, you say, I really got a crisis, I just cannot finish, otherwise I'll fail the course, you can discuss with me. There's a possibility we discuss, you have a good reason, we can postpone it, you will get incomplete, and you finish in the summer. Okay, that means I don't want anybody fail the course, but you need to discuss with me earlier, we get some consensus whether it's hopeful or it's not hopeful at all. Okay. Okay, so that's about our, the end of the lecture, end of the class. What are the major tasks we need to do? Okay. Now we are going to finish the last session on data stream mining. Okay. Data stream mining, we said, for clustering analysis, like you try to find k-median or k-means or something like that. You find good clusters. In the case of the data stream, the data flowing in and out in an infinite, context. How can we do this? Okay. The first interesting algorithm was done by O'Callaghan. Actually, it was also Modwani's group in Stanford University. What they did is they developed a k-median algorithm. Okay. The general philosophy, I can use this picture to illustrate it. The general philosophy is the data points is at the very low part. But you are not going to register the data points because there's no way you can hold all the data. What you need is just getting a cluster. You register how many points were in your cluster. Okay? So to that extent, what you did is you calculate the median. Okay? And you get a cluster, you calculate the median. You will only store like a level I median. You will never store the real data points. Okay. But you store the median. In the meantime, you store the count. That means how many points really contribute to this median. Okay. In that sense, you store some useful information of your data stream history. Okay. Then those points are all gone. Okay. What you need to do is the new data comes in, you will see whether this data is closer to which median. Okay. You put the count into this median. In the meantime, you may shift the median a little. Okay. Just to give you a simple example. Suppose you want to find a U.S. income, okay, like IRS want to know the U.S. income. Suppose you got a billionaire like a Bill Gates already. Okay, their median for those billionaires could be very high on the top, but you say they're about say 20 billionaires. You put it down there. Okay, and then suppose you got a new billionaire. Suppose Mark Zuckerberg. Okay, he got a lot of new income, get a new median. But you already forgot all the others because you cannot store every single one. Okay? It's a data stream environment. You only store the billionaire, their median. But you got a new billionaire come in. Okay, what do? Okay, you're not going to register Mark, okay, because it will be gone as well. Okay, but you will take the single node and the money, the income, add into this median. The median, the count will go a little higher. The median will also shift. Okay. For example, if Mark get more money compared to the billionaire median, the new median will shift up a little. Okay. If Mark get a little less than the average, the median will shift down a little. You can see that. But you still store those very rich people as one single node. Is that clear? Okay. In that sense, you store limit number of median value, but you actually compute all the median somehow there. Okay. Of course, if I say median, you may argue with me. The median is very, very tricky. Remember, this median is just it's like a mean. If you think the mean, probably is a little easier to think. And it simply says, the thing will be a little, shift towards to the real median, okay? But you don't need to keep all the data. Okay. Remember, in computer, everybody precise median is very hard. What they call median is just approximate median, right? Is this clear? Okay, so it's a pretty efficient algorithm because you only store, certain number, like a level I median points. You don't store anything else. Okay, but the data stream coming in and out, you don't care. You still get the right one. Okay. So looking at this, actually the team is Sharu Agrawal is a quite famous researcher. Actually, this year he's a KDD PC program committee chair. Okay, he's at IBM Research and Watson. Me, and this is my postdoc now. He's a professor in Tsinghua University in Beijing. And Philip Yu, that time he was also in IBM as a manager, researcher lead. So we forgot a substantial discussion, and we work out a new method called clustering. Okay, just to say stream, how we do clustering. Actually, this one was the very first quite impactful algorithm for IBM research. Later, IBM research got a very big contract with defense. They built a system called Stream. If you really go down IBM side, they have a flagship product called Stream. Okay, the first work actually is this one. Of course, we work together with a lot of other algorithms, published many papers. But this is the very first one. We did it in 2003. Okay. So what this one, how we designed this algorithm. Okay, you probably can look at this. Essentially, is we know you have only one pass. That means the data comes in and out. There's no way you can store all the data sets. Okay. And we have very limited space, but we want to get a high accurate, highly efficient algorithm. How we do this? Okay. We actually, these several bold method you probably can see, tilted time frame means, remember we said the tilted time frame in the early ones. If you look at the one, we have this tilted time frame even in the discussion of the, I think it's around here. Okay, this is the tilted time frame. Tilted time frame means you don't want to forget history. You still want to get some rough sketch of the history. Remember, Monwani, their algorithm is you only keep the current one. All the history will be forgetting. Okay, but in many applications, you want to see the changes. Okay, you want to see the evolution. You don't want to forget the history. So we keep this tilted time frame. Means the most recent time we make its finer granularity, and while the time goes by, the more distant time, okay, remote in the past, you make a rougher and rougher granularity. Okay, but Sharu doesn't want to follow this natural tilted time frame. He doesn't want to follow logarithmic tilted time frame. He developed an interesting tilted time frame. I probably will show you. The tilted time frame is this one. Okay, called pyramidal tilted time frame for clustering. What is pyramidal? Okay, if you think about this pyramid, okay, the pyramid means at the very top, it's a small number, and then you go down, it becomes sparser and sparser, right? So this pyramid, actually, if you think about how we define the pyramid, is this. The time coming, you get a frame of the data coming. Okay, it carries the time stamp. Time stamp at the very beginning, say time 1. Then it keeps incrementing. Incrementing means, for example, you can see this is a 16, 32. You keep incrementing. Suppose now the time is 70. Okay, if the 70 comes, what you do is you based on how many frames you have. You have 0 to 5. You have 6 frames. Okay, 6 frames. That means this D will be your number of frame minus 1 will be 5. Okay, so you can see you have frame 0 to 5. Each frame, you suppose you only have at maximum 3 slots. Okay, so you can see you have 3 slots to store the frames. Then how you can gradually, gracefully fade out the previous data. Okay, so the algorithm actually is pretty simple. It says every time you get a new snapshot, carry timestamp n. Okay. What you need to do is you mod 2 to the power of d to see what's the number. Okay, you mod it. And you get this mod, you get this number put into the right slot. For example, suppose now 71 comes. You can see the last one is 70. Suppose 71 comes. 71 is an odd number. That means you mod 2 to the power of d. Now it's 5. You mod 5, actually it's not 0, it's 1, right? You mod this one, you get a 1. Okay. If you mod this, you get a 1, you get a 0, you insert to, that means that you cannot be modded to the right. That means you cannot divide by any 2 multiples because 71. Okay. Then what you do, you insert to the frame 0. Okay. And then you say the frame 0 already has 3 slots. How do you do that? Actually, if you get 71, you insert into this one, you kick out the oldest one because you only can hold 3 frames. Okay. You kick out 65. But if you get 72, what do? 72, you mod it. Remember, 72, you mod it, I think it's, you can mod it to 8. That means you get into this 72, or insert here, kick out 24. Okay. What's the trick? Why you do that? Okay. Then after you do this, you can see the most recent, you store quite a dense one. And you get it later and later, it becomes sparser and sparser. It's automatically kick out the frame in a very graceful way. For example, you can think about this. If you check the 70, you already see its elegance because you can see 70 is stored, 69 is stored, 68 stored, 67 stored, 66 stored, 65 stored, 64 stored. That means the most recent one, almost every frame is stored. But then they gracefully jumping. For example, once you get 64, okay, you probably see you will not be able to get 63 because 63 was kicked out. 63 is an odd number, and this one already kicked out. You can see because if you have 4 slots, you can store 63. Otherwise, 63 kick out. But 62 is there. 60 is there, right? Then you see 58. 58 should be here, but it's kicked out, right? So you probably can see you gracefully, originally you have last several, at least the last 5 or 6, every slot, you store them, okay? Then you store, each one you kick out the odd number, okay, you store these. Then you kick out, those cannot be divided by 4, those cannot be divided by 8, those cannot be divided by 16, okay? It's gracefully, you make the gap bigger and bigger. So this one is a pyramidal theory time frame. Actually, this one we should credit to Shahrukh Agrawal when we got discussion. He said, I will design better one than the logarithmic one. Every time you jump, double it, that just jump too quick. Okay, so this is a pyramidal theory time frame. That's the first one. Okay. The first key point is microclustering. Okay. Microclustering, I'm going to show you what is microclustering. Okay. To say microclustering, I have to introduce another very interesting algorithm called Birch. If you took CS412, I think you know Birch. How many people do not know Birch? Everybody knows? Okay, that's good. Birch was an algorithm developed in the University of Wisconsin in 1996, okay, published in 1996. And this algorithm, the general philosophy, actually it was very interesting because the first author was Tian Zhang. When they developed this algorithm, they want to compare with our algorithm. At that time, I was in Canada. She actually sent me emails, keep requesting code, explain the algorithm. I may never know she was a girl because Tianjiang, you never could recognize it. Just by emails, there's no way. That time, there was no good web. You can't look at anybody's picture. So I was keep sending her, all the supporting material. Then they work out this paper. It happens the Sigma committee sent us to review. We actually quite like the paper because they compare with our methods, say they beat our method in a very big way. That's why the Sigma committee actually sent us the original author, say you review it to see whether you like it or it's really what their claim is true. Both Rima and me, we reviewed the paper. We think it's great. We actually say this is a great paper, it should be accepted. And here we met in a conference. I found that she was a girl. And then her advisor, Raghu Ramakrishnan, is a very famous one. Actually, I think he already is in Microsoft vice president already now. He was a professor in University of Wisconsin. And it happened, this algorithm, 10 years later, this one was 1996. In 2006, they got 10 years highest impact paper award in Sigma conference because this paper cited and followed so crazy with so many important work following this work. And we actually also follow it. Even in her 10-year impact paper award, she listed many papers. Very good papers follow this work. Actually, this IBM's paper also listed it. I mean, this clustering paper also listed as one good example to say their method can work on data stream as well. Okay. What the method is doing is this. Okay. If you explain that, it's pretty simple. You've got so huge amount of data. Okay. And if you try to do clustering on all kinds of data, it's just too big, too much. Okay. What they do is they say no matter what clustering algorithm you use or you want to use, you first need to construct a good infrastructure. The infrastructure is this. Once you get data, you actually do very local clustering. That means very similar one, you try to glue them together at the lowest level. That means the lowest level, you just look at your neighbors. You do the nearest neighbor search, you do this, you cluster them. Okay. This is, later they got a paper that just explained the philosophy is, suppose you go to a big beach, you want to cluster the sand. Of course, nobody really wants to cluster sand. If you cluster sand, the sand is just so huge. What do is you first glue the sand into a tennis ball. Okay. That means no matter how you do the clustering, you glue so much sand just into all the tennis balls, you reduce the numbers you need to consider. Okay. So you can think these are the tennis balls. Okay. But later you say tennis ball is just still too many. Okay. What do? You glue the tennis ball into a beach ball. Okay. This is much bigger. Okay. Because even you do the beach ball based clustering, you still will get good clusters. You will not miss much. Okay. So with this philosophy, their Birch algorithm basically saying when the data comes, you glue the nearby one, you forget the granularity of this sand. Okay. You just get into a tennis ball, you get a beach ball, then you cluster on the beach ball. Okay. So actually for clustering, this algorithm it carries the same philosophy. Because the data comes, you don't want to register, you don't want to remember every piece of data. So you treat the data like a sand. Okay. You just say the data comes, I try to absorb them into any existing tennis ball. Okay. Once I absorb, of course you may say that the sand comes very far away. It's fine. The far away, they form their own new tennis ball. New cluster. Okay. With this philosophy, you don't need to worry about a tennis ball level. You can even go to beach ball or something. But you need to register something at a higher level. Okay. Not too high. Okay. Then when you want to do cluster, you say, I want to get 20 clusters, like 100 clusters. Suppose you have 1,000 tennis ball. At that point, you can take those tennis ball. You say, what do you want? You want a density-based clustering? You want a k-means? You want a k-median? You want a whatever? Okay, I can take those tennis ball. I can redo the clustering. Okay, so that's the philosophy we call microcluster to get tennis ball. And then when you ask to get a bigger ball, get a bigger cluster, I do macro clustering. Okay, so that's the philosophy you can see. We say micro clustering is to do incremental online processing and maintenance. That means you never look at the sand. Every time when the new data come, you just glue them into the new tennis ball or incrementally enhance the existing tennis ball. Okay. Then at online, that means you said, I want to get 10 clusters, I want to use density-based clustering, whatever. You say this, we will take those tennis balls to do macro clustering. Okay. So you probably can see that's the philosophy, and this philosophy works really well. Okay. So that's the reason we actually got to take the CF tree, the birch method. Then we actually did this in a very nice way. Okay, that means we have online to do micro clustering to keep maintaining this birch tree, this CF tree, and in a very elegant way, because every time the data stream comes, you just modify the tree a little, And then anytime you instantiate a query, you say, I want to know now. I want to compare now with, say, 5 days ago, okay? Because you have timestamp. You have different cluster. You can merge them. You can split them, then whatever you like. So you can do query-based macro clustering. It's very flexible. Okay? And this philosophy, actually, in IBM later, they implement this stream engine. And this clustering algorithm, this philosophy actually is used in their engine. Okay, so this is a clustering. Later, this paper also cited many, many times. Okay. So now I finished all the stream mining. You can see stream mining is pretty interesting in the sense the stream is coming and going, but you can develop an algorithm to capture the most essence from the data mining context. You can find the patterns. You can find the classification models. You can find the clusters. You can do data queue. Okay, so you can do a lot of interesting things. Okay, so if you look at things, you can see for the data stream, a very important concept is tilted time frame, and we have multiple layers. No matter in data cube, we can have layer. In the cluster, we also can have multiple layers, right? So those are the things you see. Those are the many interesting research papers you may like to read. Okay. So I think we finished this one. Now we get into a new session, which actually we got more people sign up for a presentation for this session because people like this session. I think it's quite practical, quite real. We have students from geographic department. They do the spatial, temporal things all the time. And we have people from other departments as well. They really like this. I probably will introduce you the mining spatial, temporal, and the social media data. Okay. So I think you may guess where this one is. Anybody can recognize this? Yellowstone, right? That's true. Yellowstone. This is Yellowstone National Park. I actually give a talk in Montana State University, which is just 3 hours from Yellowstone. That's why I went down there. But my talk was in May, early May, before the semester ends. But in Yellowstone, early May was still pretty cold. You can see the snow is still covered with a mountain, right? But this one is not snow. This actually is, yeah, these are the, you probably can see the the smoke, and these are all chemicals. Okay. So you will see lots of geographic wonder there. Okay. So the spatial temporal things, that's one of my previous PhD students. He did this one. I'll introduce you quite a few of his work. His name was Zhijun Yin. I actually met him during the spring break, Friday. I give a talk in Google. He's in Twitter, but my previous students, they all know I went to Google. They actually are in the dinner. They get together with me. He actually is a manager in Twitter now. He is doing very good work. But I will show you, actually this one is very useful for Twitter analysis as well. You can see we got spatial data, we got temporal data, we got text data, we got links. If you play with tweets, you probably see spatial, temporal, text, and link. Is all the places, right? That's his PhD defense slides, and it's very fit to his current work in Twitter, because Twitter is dealing with spatial, temporal, text, and the links. Okay, that's the one. Nowadays, you get social media, get spatial, temporal data. You are actually all looking these several things integrate together to want to do analysis. If you just want to do data mining on spatial data, we call this one is a geospatial data mining. The people in geography are doing this all the time. Okay, but if you do temporal data, you just work on temporal data, you may do time series analysis. We had one professor interview here. He's a professor in USC. She actually did very good work on time series analysis. Her PhD thesis got that's 2007. She graduated from CMU. Her thesis got an ACM dissertation award, honorable mention. Okay, that means one of the best in computer science. And if you link spatial and temporal together, you get trajectories. There are lots of work on trajectory data mining. I had one student, Zhenhui Li. She now is a professor in Penn State. Her PhD thesis is on trajectory mining. I'm going to introduce some of her work as well. And then if you link spatial and the text, you get a geographic topic analysis. You link with temporal, you get a latent periodic topic analysis. Then you link with the network, with the links, you will get text-rich, geographic-rich information network analysis. So it's a very rich domain, and the data, the data very rare, because you actually can get tweets, Instagram, anything. You can get it now, you can do analysis. You will have a very good impact. Okay. Now we will do a little. We are not such a big class. We study a lot of things. We don't have time to get everything, but I will show you a few very interesting pieces of work. One is a geospatial pattern mining. Okay. Geospatial means you just based on the geodata and objects and the locations you want to do data mining. Okay. That mining, actually, you may want to find frequent patterns. For example, maybe this one is a city. Okay. This one maybe is a river or lake or ocean. So you can say, where there is a city, you will be able to find a very nearby, there will be a lake or river or ocean. It's almost pretty true. Your support and confidence could be very high. That means you find a city, majority of the time you will be able to find a river or lake or ocean, okay? Especially big cities. Like Chicago is by the Lake of Michigan, right? You go to Seattle, it's also by the ocean. Okay? San Francisco, Los Angeles, New York, almost anyone. Houston, all these is by the ocean or by the river, right? And some are both, like New Orleans, both by the river and by the ocean, right? So that's the reason we probably can see this is pretty true. That means you want to find something interesting as a rule. What you find is actually for geography, you may have lots of different relationships. for example, you may say intersect. For example, city may have a river right inside the city, like you go to Budapest. Okay, the river actually split the city into two parts. Okay, so that's the one. This intersects means the river intersects with the city. Overlaps, maybe like a mountain. Like you go to Vancouver, they actually have a river, have an ocean, have mountains. That's why it's a very beautiful city. And the mountain actually somehow overlap with the city because some part of the mountain already houses the districts. Like West Vancouver, the whole city is on the mountain. Okay, so that's the reason city can intersect with mountain or even with a river. Overlaps and disjoint. Disjoint means you do have some distance. So all these, the interesting thing is, when I was in Vancouver, okay, I got one student, PhD student called Chris Kopersky. He was very interested in this spatial data mining. He got in, he said, I want to find the spatial patterns. Okay. And he looked at the map, he got lots of data on the rivers and water and the city or some towns or something. Then he found, actually it's pretty interesting, he can find this rule. He says, if X is a large town or city, okay, X intersects with the highway, and then he will find X is very close to the water. Okay, like either the water is inside the city or is by the city. It's this one. He found there's 7% support. It means 7% of the world city have this features. And if you find the city is a large town, is intersected with the highway, there are 85% chance the water is very close. That's adjacent to. That means either water flowing to the city or very close to the city. And that's a thing, actually you call it, this one is geospatial rules or association. Okay. That's the first paper actually he published. It got lots of citations because people originally found an association rule just on like Walmarts, like diapers and beers, they get together. And now you find that the city, the spatial property, there are lots of very interesting ones. But not only he found this, he found a principle, how to mine it efficiently. Okay. How to mine it efficiently, he got one principle called progressive refinement. I want to see whether this one's still there. Progressive refinement means what? Means if you try to use some predicate, for example, water flow into the city or something, not all the water flow into the city, okay? Some you just buy the city, okay? So if you want to find this, you first find a general predicate. General predicate means you say close to, which may cover nearby, touch, intersect, contain, overlap, or something. That means instead of you find a very precise spatial relationship, you first make the relationship a little general, a little rough. Okay, you can cover more data. Otherwise, you may miss lots of rules, or it's very hard to find them because you don't have that much support. That means if you want to find something, you first go higher. Okay, it's more like in Facebook, you say, I want to find friends. But later you want to say, what kind of friends? Okay, whether my colleagues, working friends, or playing friends, or relatives or something. So you will see he first go high, say close to, okay, and he find a rough relationship first, then go down to refine it. Okay. The philosophy is very clear. If the rough one you cannot form patterns, you try to refine it, you will never be able to find patterns. You think about this. If the rough one, say these city and water are very close, rough one you already find this, then you will refine the detailed one, say what kind of city, what kind of water, okay, whether it's a lake, it's a river, it's ocean, and whether it's close by or next to each other or flowing into each other. Like Venice actually is built inside the ocean somehow, right? The whole thing. So you will see different features, but you need to first find the high-level rough ones. Okay, only the rough one is frequent. You go down, you find a more refined one, you will have a chance to find it. And you can filter out a lot of, not interesting pairs. That means you don't miss anything, but you reduce your search effort. Okay. So his philosophy called progressive refinement. Okay. The progressive refinement also, even in spatial one, he says, I do not need a very, very detailed algorithm. I can use a very rough algorithm. I actually will find patterns. What he used a rough algorithm is just use minimum bounding rectangle. You probably know what is minimum bounding rectangle. Okay, that means originally the river may be like a line, or lake may be different shapes, a city or a highway or different shapes. But he just used minimum bounding rectangle. Just use this bounding rectangle, shift it to find the patterns, which is very cheap because of whether you are in the same bounding rectangle. Okay, if you are in, that means you are close. Okay, you are not even in the same minimum bounding rectangle. I do not consider those pairs. Okay, so he basically using this way, in a very efficient way, both computation-wise, conceptual-wise, and then find a lot of patterns. Okay. For example, this picture is not a very, very vivid, but this picture basically shows these are the shopping centers, like these ones are shopping centers. This round one are the gas stations. These line are the roads, the major roads. Okay. You probably can see how he would like to find. He want to find the major roads has intersection, right? And he found the intersection of the highway, the shopping center, the gas station, actually is all together. He can find the rules. Means if you find a highway intersection, you will be able to find the shopping center and a gas station in a very high probability, which actually is true, right? Most highway intersection, you will find those things. But those simply says you use a rough algorithm. You can refine your algorithm later. You can see how far it is, within a mile or something, right? So that's the one called progressive refinement. Actually, later, a lot of spatial algorithm, mining algorithm, they use this principle. That's also why this paper is cited so often. This paper was published in 1996. Even 20 years, people are still citing this paper because it's the first one they use this progressive refinement to find interesting things. Okay. This one is also in Yellowstone National Park. You probably can see these are the chemicals. Okay, it's coming out. Then the tree surrounding the tree will die because the chemical things cannot the plants cannot live there. Now I'm giving you more on the trajectory patterns. That means people not only just try to find spatial relationships, people call co-location, the spatial objects that locate together. They want to find these patterns, but they also want to find the movement pattern, trajectory pattern. Trajectory means how they move. Okay. This one was actually a group of people in Pisa, Italy, University of Pisa. I actually went down there, I think in 1999 or so. I went down there. They invited me to go there to teach in University of Pisa on data mining for 1 week. Okay, they want to learn how the data mining going. And these several professors, these two other professors, these are students, they actually work out quite a lot of paper later in data mining. It's one of the data mining center in Europe. Okay. And this paper talking about the trajectory pattern mining. Trajectory pattern mining, in Europe, a lot of cities are still the street is still pretty narrow. Okay, it's not like in the U.S. you see so wide highway, get 6 lanes traffic. It's still, going through the city, then you get a traffic jam, it's a real jam. Okay, so what they want to study is, in the rush hour or something, they want to find, the traffic, how they go, how the traffic flows, where are the traffic jam places or highway sectors, at what time. So they can actually report the traffic or get a map where that time there were no Google, real time give you the traffic situation. So they want to work out using this data mining methods. And they mine this one, the pattern they got called T pattern. T means trajectory. Okay, they try to find trajectory pattern. How they get this T pattern is this. Okay, first you work out the region of interest. You can see this is one part of the city. This is another part of the city. And then you may have different interest points. Those points are the interest points. This could be, your office. This could be your home. Okay, say you want to go back home after work, but you may get a traffic jam. How do you project the traffic? You finally find, the patterns. Okay, what they do is they partition all the area into grids. Okay, these are the grids. Okay, that means partition the space into equal width grids. Okay, you get all these region of interest. Then you transform every trajectory into time annotated symbolic sequence. Simply says, you got a heavy traffic. Okay, the traffic you say suppose. Now here you get traffic is very heavy at what hour? Okay, then this one you give a number. Suppose this one is a Q. Okay, this one is R. This one is S. This one is T. Okay, you get a Q, R, S, T. You get time there. Say this is the heavy traffic in this part. Then you get a number. Then they finally transform this into the sequence, time sequence. Then based on the time sequence, they just mine the symbolic sequence, try to get trajectory patterns. Okay. So then they finally plot the pattern. Okay. So this is their trajectory pattern mining by projecting the trajectory into the symbolic sequence, QRST. Okay. Then you find a QRST this time is jammed. Okay. So then finally they plot to the map. Of course, you have to get a somewhat refine a grid structure. You probably can get a better one. But you get too refined, it's too expensive to compute, or the pattern may not show up, right? So they basically they call trajectory T pattern mining. Okay. Then I'm going to show you, my student. Jessie Lee. That time she was called Zhenhui Li. Okay, and she actually worked out a very interesting pattern called swarm pattern. Okay, the interesting thing is that people are looking at the patterns on the traffic or animals or all these things, and try to find a good pattern. There are two influential ones. One called flock, one called convoy. What is flock? If you watch how the sheep are moving, right? You know the flock, what the sheep are moving. Sheep moving usually get a crowd. They keep moving around, right? And how do you find flocks? The flock you find is you get at least M entities. If you think these are sheep, you get M ships, right? They move within a circular region of radius R and move in the same direction. That means you look at timestamp. Every timestamp, if you have a photo, suppose you have a camera, you say, every minute I take a picture. Okay, that means your time is minute. Every minute take the picture, you'll see the flock. Now it's here, now it's here, now it's here, now it's here. Then you will say there's a pattern, okay, moving that way. Then you find there are lots of objects. Every ship is object. There are lots of objects. They move in the same direction. They form a pattern. That's a flock pattern. Okay. But another one said you think all you may want to find using density based rather than you use a fixed circle. The The flock one is they use a fixed radius. Say within this radius, you just look at this, they find a pattern. Okay. But the convoy said, I do not have a fixed disk. Say this is the size, and it contains 5 objects or something, you find the pattern. The convoy said, I make the radius a little elastic. Elastic in the sense, sometimes the object may be a little far away, sometimes they are very close. You think on a highway in the rear convoy, what do you see? Of course, you will say there's a convoy, the trucks are moving. Actually, in the highway, sometimes the small car sneak inside, in between those trucks. The truck will become far, far away, right? So if you just say these are very small radius, you will not be able to catch those trucks. You have to enlarge the radius a little more. That's why they suggest this density-based clustering. Okay. So the previous algorithm, one is how to detect flux, one is how to detect convoys. Okay. Then when Jessie came, she read those papers. She says, actually, these are not quite realistic in developing patterns. And the reason is this, okay, even you think about the ships or horses, they move, not every time they will be so like an army. They always be so narrow, so crowded, moving in a synchronized way. The ships, they find some grass, they're going to spread, they're going to eat. Some will go, some will not go, right? So finally, your radius can never cover them, okay? And she actually thought about it. You will allow at some time, they do not even form a cluster, okay? And only sometime you find they are, together, they still move together. It's still a good pattern. Okay. So, and she actually finally discussed with quite a few students what's a good term to describe this pattern. Actually, people give her a very good term called swarm. What is swarm? You see the bees, how the bees moving? The bees actually, they do not move like a convoy, right? They move as they can go far away, pretty big, pretty far. If you look at the radius, it's very far. But then they may, synchronize. At a certain point, they get together. Okay. Then they go out again. Those are the swarm. Okay. And she actually says the real pattern you want to find are people moving together or animal moving together. Most time you use swarm, you're going to find the real pattern. Because you allow them to spread, you allow them asynchronized. But overall, they're moving in the same way. So this is the swarm. That means at a certain time, you take a snapshot, you'll find they are a cluster. They move together. At a certain time, you take a picture, they are far apart. Okay. Then you need to develop an efficient algorithm to find this. Okay. She actually this, of course, is more challenging, right? You have to say sometimes they are very far apart, they still say they are okay. That means only certain fraction of snapshots you can find patterns. Okay. And she developed a very efficient algorithm finding this. More interestingly, I did not show it. More interestingly, she actually got a real animal scientist. Okay, it's interesting is her software system called MoveMind really delivered to the animal scientists. Actually, I myself attended the meeting. She actually went to a very exotic place, like going to the Mount Denali in Alaska. Their meeting was there. Okay, they were among the animals, right? Those animal scientists. I actually went down to one in Pennsylvania, right inside the mountain, in the winter. They have lots of eagles there. They actually want those animal scientists from all over the world. They get a meeting right in the deep of the mountain. Okay, so what they do is they told me very interesting stories. They actually, this is a real, they need the data mining methods. The reason is this. Their sensors are very, very expensive. Okay. I probably should give I think, Davis, you are going to have a presentation, so I better give it to you instead of I keep describing the story. Okay, I'll describe this algorithm a little later. Okay, so you have you download from the internet already. You can get it. Later, I will put in the same location. Okay, same place. Anybody later you do the presentation, you send me the slides the night before. I can upload it. Actually, he did send me, but 2 months ago. I was thinking he had some update, so I did not load it. He actually told me it's the same as 2 months ago. Okay. So. Okay.
Can everybody hear me? Okay. So I'm a grad student in the Cyber GIS lab here at UIUC. It's in CSA. And mining spatial data is a huge component of what is now geographic information science. So it kind of originated with the need to take paper maps and digitize them, and that was done in the 60s, 70s, and 80s, predominantly with a large light board and a tool that was kind of like a computer mouse, and you would click every line on the map a lot of times, and you would try and generate these spatial features using a very manual digitization process. Later, this became, placed into software and much easier. But as computers got better and as the field evolved, we wanted to have be smarter about it and let the computer do more of the digitization process. And so there were some object-based feature classification methods that were presented and worked well for a long time. But recently there have been some applications of ant colony optimization method, which I'm going to kind of go over very briefly. So in extremely high resolution satellite imagery, aircraft imagery, let's say you want to extract a road network. Well, because of the number of pixels you have and the number of features in the image, a road can actually be obscured by cars, the tree cover, canopy cover, shadows of buildings, other types of ground clutter. And so it actually becomes very, very hard on really good data to get really good information out of it. But the ant colony algorithm outperforms the object-based methods that would just be looking for the shape of the roads in the imagery. The other nice thing about the ant colony algorithm is that it's computationally scalable, which is important because if you can imagine, there's an awful lot of satellite imagery available that would need this ran on it. So the way it proceeds is you pre-process the data. You basically detect all the edges in the image. And this provides a context where the software ants or agents will operate. And they'll try to move in the same general direction, and they try and line themselves up with the edges and the kind of general trend of edges around them. Then they deposit a pheromone or just a marker on the grid that says, I was here. And then the other ants tend to follow where the most pheromones are, and slowly you evolve this road network. It has millions and millions of software agents that are executed across a grid. It's not like just 3. But it does really, really well. As the results, as you can see in the results, it does much better than the kind of object-based approaches in both completeness and accuracy. So, if you're looking to try and extract information out of imagery, it's a very challenging problem, especially as the resolution increases. Another area that the field is very active in is in trying to help geographers understand human mobility. So if you're not familiar with some of the urban social theory, there's a lot of interest in trying to understand how we as people actually use resources in our city, where a resource could be education, an office space, parks, green spaces, government buildings, faith centers, whatever you can think of that could be an urban resource. This kind of captures it. The other important thing is we want to know how people use it on a daily basis, within a day, hour by hour, and also predict that behavior, because that allows planners to actually have some intelligent planning abilities, not just say, well, this is what people do now with the current city structure, but if you put in a new road, people may do something different. They may want to use the new road, and that might change the surrounding way that the urban infrastructure is used. So last year, the lab had this paper published that was where Chicagoans tweet the most. It takes Twitter data to try and assess human mobility. So what had been found is that people not only you can create the trajectories like the professor was saying, but people tend to tweet at similar places a lot. So you're going to tweet at your house a lot. You're going to tweet at wherever you work a lot. You might tweet at school a lot. But if you only go to the grocery store once a week, you might not tweet at the grocery store as much as these other places. So if you build the trajectory based on the most frequently visited locations and then associate that with land use, all of a sudden you can see where are people moving, how are they moving, and what types of urban infrastructure are they using in these new places. So the methods for this study were we looked at all the tweets for the 2014 calendar year. There was a crawler that was running for 12 months. I don't actually know the total number of tweets that were looked at off the top of my head. We then filtered it because we wanted to only kind of look at users that tweeted a lot, because that would make the analysis easy. Or this would also happen if they retweeted a lot of things. So if they're doing anything on Twitter, that's good. We applied a dbScan to identify the kind of top cluster locations of each users, and then generated the trajectories. There's really good land use data actually in Chicago. New York City is another area that has excellent land use data, and we classified it slightly. They have a lot more classes than 23, but some of them you can merge in terms of what an urban resource is. And then we assign the clusters. If you think about how you would tweet, you get to a place, you might send a tweet, I'm here at the restaurant. Well, you may be tweeting from the parking lot, not necessarily on the property that the restaurant is located at. So we had to do some kind of data analysis to try and shift the cluster positions and stuff to make sure we were associating the frequently visited locations with the correct land use types, which for the most part we were able to do quite well. But then the results were very interesting. So these are the top visited locations by urban resource. So obviously you can see residential is very popular, popularly tweeted from. There's also this other type, which if you've done lots of kind of data analysis, you know that your catch-all usually has a large component in it. But otherwise, it was very interesting because this is one of the first times we've ever really been able to look at on a intraday basis how people are using urban infrastructure. Some other interesting things from our analysis of this data is that the education, this is time of day. So you kind of see everybody goes to school. It's quite large because, one, Twitter's users are younger and they tend to be enrolled in education programs, so they're overrepresented on Twitter. But you can also see that around 3 o'clock, a lot of people go home, but then there is these kind of extracurricular activity type tweets happening. And then, of course, it drops off because nobody's at school at 3 a.m. in the morning, or at least I hope not. You also see that, the residential tweeting increases during the day from when people wake up to, later on. They get home from work, and they're going to bed, they're reflecting on their day, they're commenting on what all their friends did, some of that. The other way to look at it is, well, your top frequently visited location is residential, but what's the second top? And that's the educational services. And you can see that some of this kind of changes, you know, in terms of importance to different groups. The last thing I want to go over that we've done some work in is, you know, having a Twitter data set is great, but it takes a long time to collect enough data to do really neat things with it. So creating artificial data in some type of process that mimics Twitter's behavior is really important. And so there's been some work related to creating probability surfaces of you know, tweet events. And then identify hotspots based on, you know, you can imagine that in a city there's a lot more tweets than, you know, on a farm. There's a lot more people in a city. So when people start tweeting about something in a city versus tweeting about something on a farm, you know, it has to be above some baseline. You know, you can't just, like, if one farmer tweets something and he's the only farmer for 100 miles, that's not going to be as important as 1 million people tweeting something, you know, in a city of 2 million people. You know, it's going to be the city should kind of be a little more important because there's more people talking about that topic. That topic should be more important. So we can use these smoothing algorithms that basically it's kind of like a two-dimensional histogram extended in time, and then you apply a smoothing statistic to it. This actually area of the literature is not something I'm super familiar with, but I wanted to show the class in case anybody's kind of interested in or has this type of problem. There is some really good literature out there, and it's able to kind of detect where you know, a movie might be more popular, or you know, something like that. There's some event happening. It can say, well, this is actually a really hot event in this area. And so then in conclusion, you know, we're more than happy to collaborate with any group on campus. We're a fairly large lab, but you know, there's lots of cool stuff, and really some of the most exciting things in our field come with interdisciplinary collaboration. So that's all I have.
Yeah, I think their lab actually contains lots of data. Even, you know, our group doing research actually is using their data. They collect the geocoded tweets. I think their group collect the geocoded tweets for the last many years, maybe 5 years. Almost all the tweet data, they are geocoded. Somehow they collect those data sets for you to do analysis. Yes? Question? Yeah, the question is what's the percentage of the data has a geocoded, has a location information?
I don't know off the top of my head. I do know that most of that information is collected from Twitter's metadata. There's also ways to infer it from the actual text, the messages in the text, and there's also various other ways to do it. So it's actually more than just people electing in to provide their location. There's actually ways to infer location in other ways.
Yeah, based on my knowledge, it's a small portion are geocoded. But even it's a small portion, if you look at the data they collected, it's really, really huge. You still can do a lot of interesting things. Plus, you can do inference from other hints to infer the geolocations. I think it's more like based on the nature of the clicking, the Twitter, the company, they somehow register the geolocation. In principle, they can publish it. I don't think they publish all things.
Yeah, I don't want to speak to the specifics. I mean, if you really want to know, I could come visit us and we'll like go through it, in more detail. I can't throw out the exact number. Yeah.
Okay, thank you. So anybody did not sign the project, you should go there and sign it. Okay, thank you.